Now, this is one of the important corollaries or statements when we talk about Lebesgue's outer measure. It tells us that if a certain set is countable, then the Lebesgue's outer measure of that set is equal to 0. Now, we already have established that the Lebesgue's outer measure of empty set is 0, and the Lebesgue's outer measure of singleton sets is also 0. Both of them are countable, being empty set has no element and singletons has one element. Now, if we talk about countable, meaning we can actually, even if it's countably infinite, or we can say we can count them, so automatically, generally, it states here that the Lebesgue's outer measure is 0. So let's try to prove that here. Now, how do we do this? Let's start with this proof here. Okay, let's say let A be a countable set, so that we could actually start with the assumption set in the form, let's say A is equal to, let's say A sub 1, A sub 2, we can count the elements, A sub 3, that's A sub 4, and so on until A sub n, and still moving forward. Okay, so with this now, this set is a countable set because our elements here can be counted, and be arranged in a certain order, and can be counted even if it's infinitely many. Now, this could also be equivalent to the union of all A sub I, where I starts from 1 to infinity. Take note, if we have A sub 1, you have this, A sub 2 for n is 2, A sub 3, A sub 4, so on and so forth. So they are just the same. We are trying to do this because, as we look into later on, then the Lebesgue's outer measure of A, which we would like to show to become 0, we can now substitute A with this idea, with this entire expression. The Lebesgue's outer measure of the union of the sets of A sub I, where I starts from 1 to infinity. Okay, just like that. And when we have the Lebesgue's outer measure of a union, we actually have an equivalent form of that. Take note that part of the definition for the Lebesgue's outer measure, another implication that we can draw to that, is that once we're able to identify a certain set in this form, this is another form here. This is one of the propositions in the Lebesgue's outer measure. We have the Lebesgue's outer measure of, let's say, the union of A sub n, where n starts from 1 to infinity, is just less than or equal to the summation of the Lebesgue's outer measure of your A sub n's from n starts from 1 to infinity. I don't know if my text here is clear because I used red, but basically this is the other proposition, and since we have here the union of A sub n, in this case the union of A sub n, and we have here the union of this interval, then we can say it's less than or equal. So it's less than or equal, let me remove this, less than or equal to the summation of your Lebesgue's outer measure of your A sub i's, where I starts from 1 to n. Okay, now how about this one here? We have here the Lebesgue's outer measure of A sub I, and A sub i's are each of these entries. Take note that we're able to establish previously that the Lebesgue's outer measure of a certain singleton is equal to 0. We're able to prove this already. In short, all of this, no matter how large I is, as it runs from 1 to infinity, all of the Lebesgue's outer measure are zeros. In short, this is just equal to the summation of 0 as I starts from 1 to infinity, this is infinity rather, 1 to infinity, or this is just equal to 0 plus 0 plus 0 plus dot 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 plus 0 plus dot dot, so on and so forth, which could sum up into 0, because this is just a repetition of the Lebesgue's outer measure of all singletons, and we know this already. So with this, we can now say, cutting everything short, starting from here, you will have then the Lebesgue outer measure of set A is less than or equal to 0. Just from this part of the process. Take note, what we are trying to prove is that if A is countable, to which what we have assumed earlier, then the Lebesgue outer measure of such set A is 0. So hopefully we could reach to that. Take note that the Lebesgue outer measure function is non-negative. Okay? It's based on how we define a certain function as it maps to the interval 0 to positive infinity. Then, this means that the Lebesgue outer measure of any set A, whether countable or not, should be greater than or equal to 0. Now, looking into these two perspectives, let this be 1 and let this be 2. We can combine them now, okay, with 1 and 2. We can conclude that the Lebesgue outer measure of set A is just equal to 0, because this is only true, or this is the only statement that is true after considering that the Lebesgue outer measure of A is less or equal to 0 and the same is greater than or equal to 0. This comprises our proof stating that if A or set A is countable, just like again what we have assumed, then the Lebesgue outer measure of the countable set be equal to 0. Okay, so this is why for some cases, for the Lebesgue outer measure of, let's say, the set of natural numbers, since it's countable, automatically it's a 0. It's one of its implications. So we have learned a lot of equivalence of Lebesgue outer measure to 0. We know that the Lebesgue outer measure of an empty set is 0. The Lebesgue outer measure of a singleton set is also 0. In this case, again, if the set is countable, then its Lebesgue outer measure is also 0. By the way, please not be confused with this, because we cannot claim otherwise, stating that if we have Lebesgue outer measure is just equal to 0, automatically the set is countable. This is the only statement that is true, together with its contra positive. Because if you're going to say that if the Lebesgue outer measure of A is 0, then you claim that any set is countable, that's a converse statement. The converse statement for this is not true all the time. Okay? The only true statement here, or other form for this statement, is the contrapositive, which states that if the Lebesgue outer measure of set A is not equal to 0, then A is not countable. Okay? This is the contra positive form. We will be having probably another discussion into this, but again, I'm just emphasizing here that yes, if set A is countable, its Lebesgue outer measure is 0, but it doesn't say that if you could find the measurement or the Lebesgue outer measure of any set which will equal to 0, automatically that set is countable. Again, the converse of this statement doesn't work. Thank you very much for watching.